would you say are some of the most promising areas of physics then?
Well, in fundamental physics, in the sense of discovering new laws and things that aren't implicit in the laws we already know at some level, I think axions and dark matter. I also think we have very compelling numerical evidence based on unification of couplings that there should be supersymmetry in the basic principles of physics. Unfortunately, some people jumped the gun and said that supersymmetry has to show up at the LHC. The real quantitative evidence from unification of couplings, unfortunately, is on a logarithmic scale. So it's very difficult to say that the scale should be 1 TeV versus 100 TeV. The calculations will still happily accommodate supersymmetry at a higher scale, slightly higher scale, which is easy for theorists to write down, but very difficult to access, very expensive to access experimentally. So, but okay, and in a similar vein, proton decay. Our best ideas about unification certainly point to the instability of protons at levels not so different from the current limits. So, in fact, I expected proton decay to be discovered quite a while ago. It hasn't been. But again, it's one of these things where, unfortunately, a small difference in the theoretical calculations can make a big difference experimentally. Because in that case, it goes like the fourth power of the unification scale, and so and also in other models, it depends on the details of how supersymmetry is broken, and so we don't. But it's very, very difficult to push the theoretical predictions far beyond the current experimental limits. So I think that's an important direction to look at for fundamental physics. And then there are purely theoretical things, and that's harder without the discipline. So it's harder to put your finger on what the point is, or what. So I'm not going to. I wish my string theory friends good luck, but I don't. I can't point to anything specific that should be the focus there. But to me, there are other kinds of physics. You might call them emergent physics or applied physics, depending on your mood, or that present extraordinary opportunities that have really been revolutionized by the power of computers to do numerical experiments, if you like, and then so you can have wild ideas and test them numerically, and then hopefully also test them in the real world once you refine them, and that's kind of a two-way street. On the one hand, physics can suggest new technologies. In particular, I think maybe the most vibrant area, but there are many vibrant areas, but maybe the most vibrant area that's on a broad front is people are becoming much more sophisticated about using deep principles of quantum mechanics to design new kinds of sensors that exploit things like tunneling and coherence and entanglement to make more refined kind of sensors, new kinds of instruments that allow you to see things that you couldn't see before, even or didn't even think about before. But the technology poses questions of how you probe entanglement and things like that. technology can drive physics, and physics can drive technology, and in the case of computation, as I mentioned, computation allows you to do numerical experiments in the broad sense, including trying to build protons from pure numbers, and that's actually been quite successful, extraordinarily successful. I didn't see that coming, even though I was instrumental in getting the equations to see them solved in that way. It just came as a complete surprise to me, and but the whole world of chemistry and lies open in principle. We know what the equations are.
Mm-hmm.
Compute, do it.
Go.
Right, and the world is waiting for new materials, new catalysts, new drugs, all kinds of new things. Okay, so here you've got the equation. Let's do it, right? So that's an extraordinary thing, and it could be that we need quantum computers to do that. Computers that really use the deep principles of quantum mechanics, and it's very exciting. We could be facing a very different material world in 20 or 50 years, thanks to these developments. And it's intellectually rich also. I mean, of course, what I know the most about and what I'm most pleased with is the parts that I've participated in, and it's been a real thrill to see anyons discovered in a clear way in the last couple of years, and start to become a useful tool possibly for technology. There's a whole field of topological quantum computing that is based on anyon, but then there are also the underlying ideas have played a very important role in setting up what's called toric codes and schemes for error correction that we'll really need in quantum computers, unless the topological quantum computation really works, then you won't need the error correction. But if the toric codes are kind of a way of getting topological computation without having the anyons, but the anyon ideas are still what drives it. So that's I'm really happy with that, and it started as a complete just curiosity about originally about cosmic strings and their properties, but then take a slice of it, you get two-dimensional materials and odd properties that really have a striking appeal to a physicist, to a theoretical physicist, because they overthrow conventional wisdom. People thought you could have only bosons and fermions for a long, long time, and the idea that there are other possibilities was quite entertaining. And then again, it's come really as a complete surprise to me that they might have some use. Well, not a complete. I mean, a surprise, not a shock. I mean, anything that's buildable at a reasonable price could have some use, but I certainly didn't have the concept that they could be used for information processing, and or even initially that they could be realized in actual materials, but that came pretty quickly.
Yeah, it's funny that you mentioned these new types of materials and kind of deep use of quantum mechanics, because on another one of our episodes we actually had someone, Deblina Sakar, who works in neuroscience, developing sensors that take advantage of quantum mechanical tunneling and using that for new types of neuroscience sensors. So that's kind of exciting.